Hello everyone, welcome to the 28th episode of the series. In this video, we'll learn an algorithm to compute the basis for the kernel of a matrix. So first, let's review what we've learned so far in the last few episodes. So we learned about subspaces, which are non-empty subsets of Rn, which happen to be closed under addition and scalar multiplication. These subspaces generalize objects like lines and planes in 3D spaces. And we've encountered many sets that happen to be subspaces. For example, solution sets to homogeneous linear systems, eigenspaces, kernel spaces, image spaces, and spans. Then we learned about something called a basis for a given subspace. So a basis is a list of vectors such that every vector in V can be written uniquely as a linear combination of the vectors in S. So remember that a basis spans the subspace V and is also linearly independent. So we also learned that from every spanning set for a given subspace V, we can extract a basis out of it by throwing certain elements. And we can also do something similar with a linearly independent set in the subspace V, but we would have to add some vectors carefully. So for the first idea, we saw an algorithm in the previous episode, but for the second idea, we saw that there is no nice algorithm that is readily available. We also learned that if we have a subspace V and we know the dimension of the subspace, then every basis for a V is going to contain exactly the dimension of V many vectors. And like that tells us that every spanning set for a given subspace V contains at least dimension V many vectors, and every linearly independent set in V contains at most dimension V many vectors. And for either the spanning set or any linearly independent set, if the equality holds, with respect to the number of vectors, then we actually have a basis in hand. So the last thing I want to mention in this mini review is the 2 out of 3 rule. So we saw that if we have a subspace and a set of vectors, and we want to show that it's a basis, we only need to check 2 of the following 3 things. So the moment 2 of these are true, the third one is automatically true as well. So the 3 conditions are the set being linearly independent, the set being a spanning set for the subspace V, and the number of vectors in the set equaling dimension of V. So now in this episode, as I promised earlier, we're going to learn how to compute a basis for the kernel of a given matrix A. So let's start with an exercise to motivate the algorithm. So we're given this matrix equation, and we want to find the general solution to this. And once we have the general solution, we want to find the basis for the subspace of solutions to this homogeneous linear system. In other words, we want to find the basis for the kernel of A. So to find the general solution, we're first going to row reduce the augmented matrix into its REF. So this is, a homogeneous linear system. So we can write its augmented matrix by taking all the coefficients and the constants, and then we can compute its row echelon form. So this matrix is equivalent to the first matrix, and it's in row echelon form. We have leading ones in both the rows. So because there are no leading ones in column 2 and column 4, we let the corresponding variables, that is x and z, the second variable and the fourth variable, equal to parameters t and s respectively. And then solving for y and w in terms of t and s gives us y equal to minus 4s and w equal to t minus 10s. So as a result, the general solution can be described as this vector t minus 10s, t minus 4s, s. Feel free to check the algebra here. But then we can rewrite this general vector as a linear combination of t times the vector 1, 1, 0, 0, plus s times minus 10, 0, minus 4, 1. For the sake of simplicity, I'm going to call the first vector v1 and the second one v2. And of course, s and t are some coefficients in R. So because I can rewrite every vector of this form as a linear combination of v1 and v2, we get that the set with elements v1 and v2 actually spans the kernel of A. So the only thing that is remaining now to see that this set is linearly independent. So to see that it's linearly independent, we convert the concatenation of these two vectors, which is this, the concatenation of 1, 1, 0, 0 and minus 10, 0, minus 4, 1 into its row echelon form, and we get 1, 0, 0, 0 minus 10, 1, 0, 0, or at least that's one of the row echelon forms. But what's important here is that the rank, which is 2 for this row echelon form, is the same as the number of vectors, and therefore we get that the set containing v1, v2 is linearly independent. And because it's a spanning set and linearly independent, it's a basis for the kernel of A. So we can use the solution to the previous problem to generalize it to an algorithm to find a basis for the kernel of a matrix A. So remember that every subspace has more than one basis, and we're just finding one basis. So we start with the matrix and we put it into row echelon form. And then we write a general solution to the homogeneous linear system given by Ax equal to 0, where x is the vector of variables and 0 is the 0 vector. And we introduce a parameter for each column of the row echelon form which does not have a leading one. Then we rewrite this general solution as a linear combination where the coefficients are the parameters that we just introduced. Then the vectors in the linear combination that are multiplied to the coefficients form a basis for the kernel of the matrix A. Now, why does this make sense? Because this set that we just got is a spanning set, because every solution is a linear combination, because we can write the general element as the linear combination of these vectors. The tricky part was linear independence, and that is true because every vector has at least one coordinate where that vector is the only vector which is non-zero in that coordinate, and therefore we cannot have any non-trivial linear combination. Okay, now that we have a basis for the kernel of a matrix, we can also find its dimension. So just by the definition, the dimension of the kernel of A is the number of vectors in the basis or in a basis for the kernel of A. Now, the number of vectors is exactly equal to the number of parameters that we introduced in the general solution. And the number of these parameters that we introduce is exactly equal to the number of columns in the row echelon form which did not have a leading one. So putting all this together, we get that the dimension of the kernel of A is the width of A minus the rank of A, because the rank of A is exactly equal to the number of columns in the row echelon form with a leading one. So we have the total number of vectors in A, which is the width, and we subtract the number of vectors which have a leading one to get the number of vectors without a leading one. And that, per our discussion, is the dimension of the kernel of A. Okay, so to end this episode, I'm going to just present this little summary. So far we have seen, 5 different kinds of subspaces. I mean, we've seen a lot more than these, but these are the 5 special kinds. There is the image of a matrix. There is the span of a few vectors, the kernel of a matrix, solutions to a homogeneous linear system, and eigenspaces of a matrix A. So the first two are similar to each other, and the last three are similar to each other as well. So at this point, we have methods to find a basis and the dimension of each of these, uh, subspaces. So for the image of A, we convert A into its row echelon form, and then we look at all the columns that have a leading one in them, and corresponding to those columns, we pick the columns in A, and those vectors form a basis. And to find the dimension of this image subspace of A, we just look at the rank of the row echelon form. Similarly, if we have the span of n vectors, to find its basis, we just concatenate them, and then we're just finding the image of the concatenation, which is very similar to the first process. We put it into row echelon form. We look at all the columns that have a leading one in them, and corresponding to them, we pick out the vectors, uh, in the collection v1 through vn. And to find the dimension of this span, we just look at the rank of the row echelon form or the concatenation. So we just saw how to compute a basis for the kernel of a matrix A. So we basically write the matrix in a homogeneous linear system. We write the general solution, use the linear combination, and pick out those vectors, and that gives us a basis. And the dimension of the kernel of A, as per our discussion, is the width of A minus the rank of A. Now, solutions to homogeneous linear systems and lambda eigenspaces of A are similar to finding a basis for the kernel of a matrix A. So for homogeneous linear systems, we just write the coefficient matrix and compute its kernel, and from there its basis. And we use the same method as we use for the kernel of A. And again, the dimension would be the width minus the rank of the coefficient matrix. For the lambda eigenspace of A, we compute the matrix A minus lambda I, and then we try to compute the basis or a basis of its kernel. And we again use the same method as we learned in this episode. And for dimension, again, it's the width of A minus lambda ID minus the rank of A minus lambda ID. And with this, I would like to end this episode. Hopefully things were clear. I will see you guys soon. Up until then, happy learning.